I'd like to acknowledge that we are gathered today on the Beedle clan territory of the Wet'suwet'en Nation. It's a great place to live and play. Thrilled today to have Matt presenting. He's been involved over the last 4 years with community-based research on Kathlyn Glacier, and we have the chance to hear from him about what's happening. He works at Coast Mountain College as an instructor, a community adventurer, has 2 kids that he gets up to all kinds of things with, and it's great to have him. So welcome so much to you, Matt.
Thanks, Tom.
And I would also like to acknowledge that our setup today and being able to record and Zoom folks in so that they can hear as well is in large part thanks to the Bulkley Valley Community Foundation and the Bulkley Valley Credit Union. So thanks very much to them for their support.
Great. Thanks, everybody. Glad to see you all here. And it's a real pleasure to talk about the glacier that's in our backyard, the glacier that really is a backdrop for a lot of what we do in this valley. What we're going to cover today is, as Don said, last 4 years of myself and a number of volunteers helping to start to monitor Kathlyn Glacier and really see and measure, quantify how it's changing. We'll connect that then to why it's changing, what's going on in our climate, what's going on the surface of the glacier that's driving that change. We'll then get into models of future change and connect that to the Toboggan Creek watershed and how the melting ice is an important component of Toboggan Creek, and kind of use that as a model to try to understand what we're faced with in the coming decades as we lose our masses of snow and ice. Right? So that's kind of where we're going in this talk. This work isn't possible without a bunch of people carrying heavy loads up the Glacier Gulch Trail, helping me carry large, pointy, heavy metal objects and long PVC pipes and other things. So if there's a number of you in the crowd today, could those of you that have helped me stand up, or if you're standing up already, raise your hand. So we've got Aaron and Sean in the back. Amy and Liam, stand up, Amy and Liam. And Winter. We've had like 14 different people come out and help out. So thank you so much. And yeah, this work can't be done without a lot of sweat and sore muscles and time and effort. All right, this is my backyard glacier. Sorry, I paused there because I'm remembering a story. When I defended my PhD research, I thanked all my volunteers for like 18 trips up to this one glacier over the course of, I think it was more 24 trips. Anyway, I started crying at the beginning of my talk. And my committee was like, it's only bad if you cry at the end of your PhD defense. So the beginning is fine. So anyway, if I get emotional, sorry, I've been doing this for a long time. So yeah, this is my backyard glacier. I grew up in Juneau, Alaska. That's a picture of me on the left in 1993. And then 30 years later, that's my son, Finley on the right. And this was important in inspiring me to what I did, studying earth science, having this amazing thing in the backyard. But these glaciers are this amazing ruler, this amazing yardstick that we have to visualize and see climate change. We don't really have much like that in the natural world. Climate change is this big, kind of obtuse, abstract thing that's going on and slowly marching through time. The definition of climate is greater than a 30-year average as defined by the World Meteorological Organization, right? It's a long-term thing we're looking at. And it's hard to visualize, but having something in your backyard like a glacier is impactful and helps us see that, quantify that, really compartmentalize that and understand that change moving forward. So this was instrumental for me, having this backyard chunk of ice and got me moving forward. And moving to Smithers, my family and I've only been here for 4 years. We lived in Terrace for 15 years before that. And so when I first came to Smithers, I was excited. I can walk up to a glacier in an hour and a half. That is amazing. It's not very common to have a glacier that's so accessible. And that's a big part of glacier research and a big challenge with glacier research is accessing the ice, getting there. Oftentimes it requires thousands and thousands of dollars and hours of helicopter flight time. So to have a glacier in the backyard that we can walk to is really important. And I had this kind of idea that, yeah, let's start monitoring it. Let's walk up there and let's study it. To kind of set the stage, the context of where we are, where our glaciers on Hudson Bay Mountain live, I want to zoom out, first of all, to the entire coast mountains. So in blue here, we've got southern part of BC, northern part of BC, southeast Alaska here, and all of the glaciers in blue of the coast mountains. Right, so a little bit of context, a lot of moisture coming in off the North Pacific, hitting the coast mountains, dumping a bunch of snow, and that is the foundation, if you will, for all of our glaciers in the coast mountains. And when we start to try to understand glaciers, especially with respect to their contribution to water, we think about, or need to think about, what watersheds are they in? So these are the large primary watersheds within the coast mountains. So to the north, we have the Taku and the Stikine and the Nass. To the south, we have the North Coast and the South Coast Mountains kind of all lumped together there. And the story there is, and you can see this visually with the larger chunks of blue, is that there's a lot of big ice to the north and to the south, right? A lot of our big glaciers are further north and further south, higher, big, broad, mountainous plateaus, further north, higher latitude, a bit colder. And then in the middle, we've got the Skeena, and it's a little bit different. You can see this from the kind of smaller blue dots in the middle of the coast mountains there. Our watershed is populated more by smaller masses of ice, right? So it's about 1.5% glacier covered, the entirety of the Skeena watershed. And our average glacier size is about 0.6 square kilometers. So relatively small compared to the glaciers to the north and south in the coast mountains. Zooming in, however, we need to break that down more so on the terms of other watersheds, other basins within the Skeena. So even though the Skeena is only 1.5% glacier covered, there are other basins within the watershed that have a higher proportion or a higher surface area of glaciers. So for example, in the lower Skeena, where we have a lot of our bigger ice masses, we've got watersheds such as the Kitsim-Kalem, which is 6.4% glacier covered, 145 square kilometers of ice. That's the most heavily glacier covered watershed in the Skeena. These kind of mid-basins here, the Zimowitz, the Wet'suwet'en, and the Telkwa. And then up in the upper Stikine and the basins that flow into the lower, into the Babine River as well. So we have interesting differences and important differences within these different watersheds, right? And this is going to be important at the end when we're going to talk about basins and how we think about watersheds moving forward in an era where we're losing water from land, and it's moving into the oceans as temperatures rise, snow and ice melts. All right, so zooming in a little bit further from here, we're going to zoom in right about here on the edge of the Telkwa and Zimowitz watersheds to where we are. And this is the Toboggan Creek watershed. So out our backyard, just to the north a little bit as you go out Highway 16. As of 2025, we had 3.8 square kilometers of ice in these three glaciers up on Hudson Bay Mountain. And that represents about a 2.9% glacier cover for all of Toboggan Creek. And again, we'll come back to this at the end after we've kind of looked at the story of glacier change to think about how this ice change is going to impact Toboggan Creek and how we need to think about that proactively in terms of a water management practice. 3 individual glaciers up on Hudson Bay Mountain. Today, we're going to be focusing mostly on Kathlyn Glacier. There's also Toboggan, and this little one, I asked Sean the other day, is there a name for that? Anyone else know? I'm just calling it Pocket Glacier. Just for ease of reference. I know this has also been referred to as Hudson Bay Glacier. There are other names. I'm curious to learn about the indigenous names as well, the Wet'suwet'en names. Say it again. Blue Lakes. Cool, thank you. Yeah, so I'd really like to, I'm going to refer to it as Kathlyn today, but I'd love to hear from all of you and talk about what we should be referring to these bodies of ice as. Okay, so that's kind of zooming in from the coast mountains all the way down to Hudson Bay Mountain and where our glaciers reside on the landscape. Okay, all right. Another point I want to make is thinking about Kathlyn Glacier, the glaciers on Hudson Bay Mountain, and how they represent a larger whole within the broader context of glaciers of the entirety of British Columbia. So this is from a study by Tobias Bolch and others at UNBC from back in 2010. It was the first complete glacier inventory of all the glaciers in Western Canada. And there's a lot of data here. We're not going to go through all of it. We're going to look here at this little plot here for glaciers of the Central Coast. And specifically, I want you to see just this big, tall, gray column right here. And these gray columns are showing the surface area in a particular glacier size class. So the important thing here is that this size class number 4 is 1 to 5 square kilometers. So the vast bulk of all the glacier ice within the Skeena and the coast mountains, the Central Coast Mountains, are glaciers that are relatively small, between 1 square kilometer and 5 square kilometers, meaning that Kathlyn Glacier at about 2.4 square kilometers today is kind of smack in the middle. It's a nice representative glacier for what's going on for the larger bodies of ice within the Skeena. All right. All of you have a much longer lived history with Kathlyn Glacier than I do. I want to acknowledge that, and I'd love to learn from all of you, both today and also moving forward as hopefully this work continues. But I love this quote from Julie Cruikshank in her book, Do Glaciers Listen? The impact of glaciers on regional history lies not simply in their immense physical presence, but also in their contributions to social imagination. So we in the Bulkley Valley and people who've lived in the Bulkley Valley have this unique, important, valuable connection with Kathlyn Glacier, whether it's seeing it from afar, recreating on it, mine exploration on it or around it, what have you, hiking up the mountain, looking down on it. We all have this lived relationship with the glacier, and that can be a really powerful thing. The other thing is there is, of course, other perspectives for understanding glaciers, understanding glacier change. Another quote from Julie Cruikshank that gets more to an Indigenous perspective on glaciers and ice. This is referencing more peoples closer to the St. Elias Mountains. Athabascan and Tlingit oral traditions attribute to glaciers characteristics rather different from those discovered through science. Glaciers have long provided travel routes that enabled human connections between coast and interior, and they are characterized by sentience. They listen, pay attention, and respond to human behavior, especially to indiscretion. And I want to bring that up too, that what I'm presenting to you from here forth in this presentation is something couched in Western science. And I'm not purporting to say that Western science has all the answers. It's one way of seeing the world, right? And there are other ways to see the world as well. From here on out, we're going to look at the science perspective of what's going on at Kathlyn Glacier. So first of all, a little bit of glacier anatomy for some terminology. This is not Kathlyn Glacier. This is Castle Creek Glacier near McBride, BC, where I did most of my PhD research. But a nice overview to look at some characteristics and some important anatomy of glaciers. We break down glaciers into a few different broad regions, and these are important for understanding their health and how they change through time. So first of all, high up, highest elevations, we have the accumulation zone. This is where you have the bulk of seasonal snowpack that falls and is ideally retained through the summer, where you're getting contributions to your glacier bank account, if you will. Okay, so snow coming and being retained high up in the accumulation zone. And down below where it looks dirtier and blue and gray, this is the ablation zone. This is where all that seasonal snow is melted and you're losing ice. Okay? And in between, you have what's called the equilibrium line altitude, this line that demarcates gain of mass above and a loss of mass below. And then at the bottom, we refer to this, a lot of terms for the bottom end of the glacier, but I will be using the word terminus, right? So you'll see some of those words in this presentation and some other figures that reference these terms. One thing important to note is, if you've ever had the opportunity to fly to Vancouver on a nice clear day at the end of summer and you can look down at all those glaciers, you can do a pretty good assessment of how the glaciers did that year by just looking at the proportion of the glacier that's covered in a bright white surface. And for a glacier to be in balance, meaning that it didn't lose mass, you need to have about 60% of your glacier covered in seasonal snow. We haven't had that for quite some time. And probably a lot of you have gone up in the mountains or flown over them and seen that. I've witnessed that firsthand. Okay, we're going to go through some data for Kathlyn Glacier. step by step in terms of a number of different ways that glaciers change. And the first of which is thinking about and quantifying mass balance. So mass balance is this balance between what you gain in the winter months, that accumulation, that's the seasonal snow that we need to be accumulating now. And then in the summertime, we get a certain proportion of melt. The snow line goes up, snow line and ELA go up. And ideally, you have some area of accumulation and some area of ablation or melt. Okay? And we can go out and we can physically measure that. Okay? If we go out in the ablation zone, we can measure how much this melts, and we can go up here in the accumulation zone and measure how much we've gained. And it looks something like this. In the ablation zone, we drill stakes in the ice, and then we come back a year later or a certain amount of time later and see how much ice has then melted and exposed the pipe. So this is up in Gittinyao territory. This is Sean Fraser. This is from this past fall, and this is showing the some 5 meters of melt near the toe on that glacier. If or when you have retained accumulation, we dig down, we dig snow pits, we measure snow density, and then we're also doing probing all over the accumulation zone to try to assess how much gain there was in terms of a water equivalent. So that's what this field work looks like in practice. For Kathlyn Glacier, for the last few years, you're only going to see stakes. And the reason is we haven't had any retained snowfall at the end of the summer. There have been little pockets of it up against the cliffs that you may have seen if you've hiked up and looked down or flown over. But in terms of the broad upper accumulation zone, we haven't had retained snow accumulation in recent years. So zooming in on Kathlyn Glacier, we have this network of 4 different stakes at this point, roughly on an elevation gradient going up the glacier. So your amount of ice that melts reduces or decreases as you go up, as it gets colder with elevation. So we want to get an elevation gradient. So a lower stake, a middle stake, and an upper stake. And then we have one over here now as well. So we go up, and these are some of the Derek Wilmot's Climb High students. Go up and drill in and place our stakes. Oops, one more time for good measure. Okay. And place our stakes, and they look something like this. If you've hiked up there, hopefully you've seen these PVC pipes sticking out of the ice. And this is in 2023, and we placed this stake. This was the first stake we placed, Aaron and Michael and myself, on October 15th of 2022, and the ice surface was up here. And so this, we came back a year later. This is at the end of the melt season, September 22nd, 2023. This is my son, Finley, measuring that. And so that is what was exposed when we placed the stake, and then the ice melts around it, revealing, and then there's 2 measurements. You take the difference, 2.16 minus 0.14, 2.02 meters of ice melt. Important to note that this is at stake 3 at the uppermost part, this uppermost basin of the glacier. This is the part of the glacier that should be gaining snow, not losing ice. Okay, and so this is a big part of the story of what's been going on in recent years with this dramatic loss of ice. So this is what this looks like in terms of surface mass balance. We have these stakes, we go up repeatedly, re-drill them, and measure as the snow melts out around them. As a little indicator of how much ice you can melt in short order and the relationship to what's driving it in terms of climate, this is from this past summer. Amy and I went up on August 8th, and we had to re-drill the stakes. The reason being that we're getting too much melt and the stakes are melting out and falling over. So we got to go up halfway through the melt season, replace them, and then re-measure again. So we did this on August 8th, and this is how much was exposed. We went back at the end of September, and this is how much of that same stake was exposed over the course of a month and a half-ish. So there was 0.5 meter exposed August 8th, and then 3.38 meters exposed. So that represents a change of 2.84 meters, 6 centimeters per day. And if anyone remembers, the beginning of last summer was cool and wet. It was shaping up to be a pretty good year for glaciers last summer. And then end of August hit, and we had a really long, dry, warm spell. So we had 17 days running in Smithers where our max temp was greater than 25 degrees C, a long, dry, hot period. And that's what drove this really dramatic mass loss. So hopefully showing in short time, when we get particular weather conditions, we can get a lot of ice melt. And kind of summarizing the stake measurements for the past few years, this is our high stake, stake number 3, and our low stake, stake 1. And down here is just the range of values we've gotten in the past few years. So between 1.8 and 0.9 meters. In this case, I'm showing this in water equivalent units. And then here at stake 1, a maximum of 5.4 meters of loss to a minimum of -4 meters in 2025. And what we can do is we can take these point measurements and we then assume them to be representative along this elevation gradient. And we can apply that for the entirety of the glacier surface. So down near the bottom of the glacier, we're getting roughly -5 to -4 meters of melt. Up at the top, -1.8 to -9. And if we integrate that across the entire surface area, this is the type of volume loss that we get. Okay, and we're talking on the order of, this is 2.8 million meters cubed to 5.2 million meters cubed, okay, in a single summer. That, if you average that across the entire glacier, you get what's called the specific balance. And the idea of this is if we averaged out that balance, this is the amount of vertical loss in terms of water you would get across the entire glacier surface in a given year. So in 2023, we averaged 2 meters of water melting coming off of Kathlyn Glacier. And it changed to 1.6 and 1.1 in 2024 and 2025. Okay, these measurements compare well with other reference glaciers through the Coast Mountains. So this map again on the left, this is where we are right here. And then we have these 3 important reference glaciers in the Coast Mountains where scientists have been doing similar studies for decades upon decades. So the Place and Helm Glacier down near Squamish and Whistler, Lemon Creek Glacier up out of my hometown in Juneau, Alaska. And these are the data as supplied by the World Glacier Monitoring Service for the last 3 years. So comparing Kathlyn to what's happened at Helm, Place, Lemon Creek Glacier, and then this average of all WGMS, this is the average of all glacier data submitted globally around the globe. And so what I'm showing here is that this trend of high melt that we saw here at Kathlyn in 2023 was also seen across the globe and within our region, and then a slight, a little bit less melt in subsequent years after that. So these early measurements we're getting, they're in the ballpark. Okay, showing that what we're measuring is not outlandish by any means, and definitely fits within this broader story of glacier melt, both within the region and across the globe. All right, second way in which glaciers change and in which we monitor them. So first of all, again, we've got this accumulation in the wintertime. We've got melt in the summertime. And if this just happened without anything else happening, this would build, and this would shrink, and our glacier would be straight up and down. And of course, you can't have that. And so something that's missing is flow, this redistribution of mass from high up to low down. And the balance of how much is lost here through ablation or melt at the terminus of the glacier, that juxtaposed against the amount that's being replenished through flow gives you either a recession or an advance. Okay, and we can measure that quite clearly from photos, from going out and measuring it just with a measuring tape. We can measure this from satellite imagery. And so this is what that looks like in terms of surface area change for our 3 glaciers on Hudson Bay Mountain. The way I've done this, so 1900, this is the green line. This is based off of a little ice age maximum extent. So we can go out and you can map the lateral moraines, these deposits that the glaciers have left behind, the trim lines where trees were, to get a good understanding of where glaciers were at the maximum of the little ice age, which in this part of the world was roughly around 1900. It varies somewhat, but roughly around 1900. So back then, we had about 3.604 on Kathlyn, and today it's gone down to 2.4. Right? All told, on Hudson Bay Mountain, our 3 glaciers combined have gone from 6.244 square kilometers down to 3.815. A main takeaway I want you to get from this is this rate, this change in terms of a % per year for both Kathlyn and Toboggan glaciers. And the main takeaway here is that it is accelerated in recent years. Okay, more than a doubling, or right about exactly a doubling for Toboggan, and a little less than a doubling of the recession rate in the last 20 years compared with previous periods. So the amount that it's pulling back in terms of surface area has accelerated with time. And this is, again, a mixture of, so glaciers, 1975. This is from the TRIM mapping project, provincial TRIM mapping project. And then in 2005, this is the Tobias Bulch Glacier Inventory. And then this red line is a mapping that I did from recent satellite imagery for this last summer. And this same story is playing out across our region as well. So this data is from Alex Bevington and Brian Menounos, again at UNBC, and they were able to look at all of the glaciers in Western Canada, in BC. And again, the primary story that they're telling is post-2010, we see this acceleration of recession. So Kathlyn Glacier is not doing something unique. It is behaving as the other glaciers in our region are doing. The rate of recession is accelerating. Another way we can measure this, and a more accurate way to measure this, is to do this annually and in the field. And this is a really cool story. Some of the longest glacier records on the planet are from farmers in Iceland. People that live close to glaciers, have a backyard glacier of their own, and more than 100 years ago now, started measuring the distance from a cairn, a pile of rocks, with the measuring tape to the glacier edge, and then going back the next year, doing it again and taking the difference. So some of our longest records are these very simple measurements carried out year after year after year. And so we've started this at Kathlyn Glacier as well. We've got a couple of cairns marked with PVC pipes up there in the glacier forefield. And here you see the Climb High students this last September measuring the distance along a particular bearing here to the glacier edge. We have another station over here doing that. So we can measure this, and we can also measure the average rates from these. So on the next data you're going to see, we can also get average rates of recession from the satellite images and air photos as well. And this is what that looks like over time. So going back to that position at the Little Ice Age maximum, roughly year 1900, we averaged about 6.9 meters per year of recession here to the mapping in the mid-1970s. Then it slowed a little bit, but still receding on average, advanced a little bit. In the last couple of years, our recession has increased quite dramatically. So 11 meters in 2024 and 16 meters in 2025. So we see it pulling back more in recent years. And this connects to a story with a local place that we're all familiar with, Twin Falls. A historic image here from the Bulkley Valley Museum, seeing when the glacier was pretty close to that Little Ice Age maximum, tipping over or starting to tip over the cliff that you see if you're out there observing the falls. And we've had this phenomenon, these twin falls, for many decades. So ice melt coming off here to the left and also here to the right. And as many of you know, probably that's changed a bit in recent years. A couple images to kind of show you how and when that likely changed. This is a BC provincial air photo from 1990. If we zoom in on this, here's the glacier edge here, and you see the dominant melt stream here, which is the one that's at present as well. And then you still have this melt channel here coming off of this lobe of the terminus and being able to melt over this and come down this bedrock here. Picture of me taken by Morgan Height. My first time to the glacier was in 2011. Morgan took me up there and we did some surveying of the glacier. And I put this in here not to show you how much more gray is in my beard. But in the background, you see this stream. And this is that other side of the glacier. So in 2011, we still had the glacier edge here. And we had a stream melting and coming over this bedrock knob and flowing down. So 2011, we still had that melt channel on that side of the glacier. And then this is from August 8th of this year. That last photo, pardon me, that last photo, you can see kind of this big rocky outcrop right there. And that is right over here. So in 2011, the glacier edge was up and on top of this bedrock knob, and still the meltwater was able to go down that far side. Since then, it's pulled back, and we've got this bit of a bedrock ridge here that's separating the glacier from where it used to spill over. And so now all of the water is being redirected here into this channel through this one pinch point right here and off the one side. So from here on out, unless something dramatic changes, that right-hand fall is going to be ephemeral. It's going to be a seasonal phenomenon when you have seasonal snow up there that can melt and drain down that side. Later in the summer, once the seasonal snow is gone, we're just going to have the left-hand side. So a product of the glacier receding and revealing this new topography, this new landscape beneath. All right. Third way in which glaciers change in ways that we can measure it. So again, we've got the mass balance, we've got snow coming in the winter, we've got melt in the summer, we've got flow, and then we've got either a thinning or a thickening all across the glacier surface. And we can physically measure that thinning or thickening through satellite imagery, various remote sensing technologies. We can physically walk across it with a survey-grade GPS, and we can measure the height of the glacier and difference it from other heights to get a thickening or a thinning. And this map on the left shows elevation change from the TRIM DEM. So this is, again, the provincial digital elevation model. And this is it's compared with a 2008 ALOS World 3D 30-meter DEM. And so if we difference those two heights, we get this type or this amount of elevation change. So the darkest reds here at the terminus of Toboggan Glacier, you're getting a mass change of between 70 and 80 meters of loss over that 33, can't add, 25, yes, 33, I can't add, period. Okay. And you see the loss extending all the way up the glacier surface. We do have some areas where you do see a little bit of mass gain, but all told, it's a story of mass loss across the glacier surface and on the order of for the bulk of the ice there, at least 30 meters, 20 to 30 meters in the yellow colors, and down upwards of 70 meters near the lower parts of the ice. So to quantify this a little bit, the total amount of mass loss over that period, that 33-year period, is 42 million meters cubed. And to put that in swimming pool units, if you take the rough volume of the Smithers swimming pool, that would be about 85,000 swimming pools worth from the terrace, or excuse me, the Smithers swimming pool would be equal to about 42 million meters cubed. That averages, so this average loss right here, minus 14.5. So if we average this across the whole surface, it'd be about minus 14.5 meters of lowering. And if we take that, if we divide that by the total, the 33 years, we get an average loss every year of about 1.2, 1.3 million meters cubed, or roughly 2,500 swimming pools worth of water coming off the glacier every year, averaging about 0.4 meters a year of water across the entire surface. And if we think about this in terms of discharge, how much did that equate to what's going on in the streams down below? That equates to about 0.16 meters cubed per second. If you're a hydrologist, you're interested in those numbers, and we'll show those again at the end to connect that to some stories going on in the Toboggan Creek watershed. The picture on the left is Michael Nelligan with our radar unit that we were up there with this past fall, which also had a survey-grade GPS on it. So we were walking around doing a bunch of profiles on the glacier, and we could measure surface elevation and then compare it with that same 2008 DEM. So what you're seeing here, all of these blue dots are a point on the glacier where we compared the surface height as measured this past September with the digital elevation model from 2008. So this would be down near the toe of the glacier and then up near the highest parts of the glacier. So in that period there, period of 17 years, we're going from losing about minus 40, 45 meters of ice down near the terminus to losing about minus 5 meters of ice up near at the top over that period. The gray bubbles here are averages for these different elevation ranges, and all the blue dots are individual points. So for that period, the total amount of volume is about 39 million meters cubed, or an average about 15 meters of lowering across the whole glacier. And as an annual average, that's about 0.9 meters every year across the surface of the glacier, or roughly 4,600 swimming pools worth. And in terms of discharge, again, this is what that looks like coming out through that little bedrock plume there that's channeling all the meltwater today. All right, so to put all those three ways of measuring volume in context, I want to compare these and look at these over time. So from 1975 to 2008, we have the two digital elevation models, week and difference, to show elevation change. From 2008 to 2025, we have the digital elevation model from 2008 and the observations from our GPS. And then in the last 3 years, we have our mass balance measurements, or a direct measurement of the amount of water being lost. And this is what that looks like through time. And similar to our story with recession, with area change, we see this accelerating with time. So for an earlier period, we were losing on average about 0.4 meters surface lowering. And then in recent years, that's averaged more about 1.7 meters of surface lowering per year. And in terms of discharge, in terms of how much water is coming down Glacier Gulch, it translates into amounts like these. And here you've got seasonal discharge. So most of our ice melt is coming down in the months of July, August, and September after the seasonal snow is melted. And we're primarily melting snow and ice in that one period of year. That's when all of this, or the vast majority of this volume, is coming down the mountain, is in that one melt season, end of summer and into the fall. And we see this quite readily with our own eyes. We see this as we hike up there. We see this also in repeat photos. We see it from the Telkwa High Road where this photo was taken. So over time, seeing that quite dramatic, really extended early 20th century position back to about 100 years afterwards. I hiked up to the ridge looking down on the glacier. So another historic image from the Bulkley Valley Museum. This one's from 1938 to 2022. And then the copies of these next two I have on the wall over there, you can look at afterwards a little more closely if you'd like. So we have a couple of repeat photo stations we've established right near the terminus to take images every year to document the change visually. And this is what we've seen just in the last few years as the glaciers pulled back. So one interesting thing to note, this new small lake appearing, and you can really see the thinning here. And then this one in particular too, taken down near the lake from 2022, our first visit up there a few years back to just this last September, pulling back, of course, but then the thinning is quite marked. And again, that thinning that you see visually here, that's that roughly 4 to 5 meters that we're measuring at that lowest, most stake every single year, piling on year after year. All right, what's causing this? Why are we seeing this acceleration? Why are we seeing mass change? And there's a few key parts of the story. One of them is increasing melt season temperature. It's getting warmer. Probably no big surprise there. I was surprised at how clear the trend has been for Smithers in recent years in terms of our summertime temperature. So this is July, August, September average temperature, and it's gone up quite markedly in recent years. And one thing to point out is this 4-year period we've had the last 4 years. We haven't really seen anything like that in the historic record. Typically, our weather patterns are more stochastic. We get a warm summer, we get a cold summer, warm summer, cold summer. We do have this one clump of time here back in the early 2000s where it was colder for a few years in a row, but we haven't seen a number of years where it's persistently warm. So that is anomalous and something we haven't seen before and key in driving the amount of melt we've seen. The other thing is decreasing winter precipitation. So things are getting drier. Our total amount of precip here in Smithers is getting drier. This is total precip for the months of October through March. So the time in year when typically when it's precipitating, it's falling as snow up there. And that amount has been decreasing quite readily in recent decades. So we're getting less of that recharge in the wintertime and more of the loss in the summertime. The other thing is the surface of our glaciers is changing. It's getting darker. All right, typically ice and snow is highly reflective. Incoming solar radiation bounces right back off. Unfortunately, with ash and soot from forest fires, that is contributing a lot to the darkening of our snow surfaces and our ice surfaces. Over time, you also get this accumulation of debris at the surface from high melt rates. So within the ice itself, you have debris. You have little bits of rock, little bits of sand, and as the ice melts, all that material is slowly moving its way up to the surface, or I should say the surface is moving its way down, and all of that's being exposed and accumulating at the top. And then year after year, if we don't get that heavy winter snowfall, we're not getting that kind of refresh of that bright, shiny white surface. And so the net result is that our glaciers are getting darker, which then they absorb more incoming solar radiation and they melt faster. So really a three-part thing that's really been driving change in recent years. All right, I want to show you now where we're going, what's likely to happen in the coming decades. And we're going to look at the Skeena as a whole first, and then zoom in on Kathlyn and then the Toboggan, and then we'll wrap things up. Okay, so going back out to the entire Skeena, this is some modeling that I've done using the Open Global Glacier model. If you're familiar with a little bit of coding and want to play around, this is totally open source. You can go do your own glacier modeling. Pretty awesome tool. These models here are showing glacier loss for these lower Skeena basins. We're going to zoom in on some of these in just a second. These are from the Zimowitz, Wet'suwet'en, and the Telkwa, and these are from the upper Skeena and Babine. A primary story you can probably all see is that all of the glacier models are forecasting a dramatic recession, if not a total glacier loss by the end of the century for the entirety of the Skeena. Now, there are some important differences within these basins. These four basins are the ones that are not going to be losing the glacier ice as fast. Okay, these are the positive stories, but still you see most of these trending towards a total glacier loss by the end of the century. This is volume on the y-axis and 2100 out here on the far end of the x-axis. And here I've just highlighted the forecasts of the percent glacier ice remaining by mid-century. Each of these lines are for different what are called social economic pathways or their climate scenarios. They're guesses as to what humanity is going to do in the future. The blue line is we get our act together. The red line is we don't get our act together. And the other two are somewhere in between. The takeaway here is that our glaciers are out of phase with present day climate. They're going to melt, and they're going to melt fast. They already are, and it's going to continue. I'm not going to sugarcoat it. That's what we're looking at. There are, though, going to be basins that are unique and different where we need to manage them in a particular way. And that's going to be a takeaway I get to here in the coming slides. So those are some of the basins where we've got more ice that are going to be a little more resilient to mid-century and to the end of century, and where it's likely to have some glacier ice remaining even beyond 2100. These are some of the basins that are not going to fare as well. So again, you see that dramatic loss of ice to mid-century, and then kind of a slow petering out. A few places where you may have some ice remaining, like in the high elevation reaches of the Wet'suwet'en. And this is what the story looks like for Kathlyn Glacier on the left and Toboggan Glacier on the right. Yeah, it's not a great story. We are going to be losing our glaciers on Hudson Bay Mountain, and quite rapidly. The model does, however, forecast in the we get our act together scenario that we likely will still have some ice on Toboggan Glacier by the end of the century. And the reason being, it has a bit of a higher accumulation zone at higher elevations, whereas that lower upper basin of Kathlyn Glacier is a bit too low elevation-wise, with this big, broad plateau that's lower than the upper reaches of Toboggan. However, there's a bit of a good news story here to turn this around a little bit about Kathlyn. So this last year, we went up with a radar. This is Liam and Michael and Jack bringing the radar back down the glacier. And the goal was to try to measure the volume, the thickness of Kathlyn Glacier. And we'll zoom in here on the image on the right. So this is a 3D image. The light blue here is the outline of the glacier itself. And these lines here are our profiles that we did with the radar. Darker blue is deeper. Yellow is shallower. We measured a max depth here just below the big ice fall of about 120 meters. And up here in the top, before our batteries died, we measured between 80 and 90 meters of ice thickness. And if we average all of this, we get an average glacier thickness of about 53 meters of thickness. Down to the terminus, less than 40. That's the part that's going to be receding, pulling back in here in the near future. This results in a total volume of Kathlyn Glacier of 132 million meters cubed. And the good news is that is bigger than what the models show. So these global models use these simplistic modeling algorithms to be able to apply the model very broadly. And this is pretty characteristic. A lot of studies that have looked at glacier thickness have shown that the models underestimate total volume. And we've found here that it underestimates it by about 28%. Ben Pelto and others at UNBC measured volume of basins or some glaciers in the Columbia Basin, and they found an underestimation of 38%. So the good news is there's more ice up there than the models think. So that's going to prolong the life of Kathlyn Glacier and some of our other glaciers. But it's not going to prolong it by a lot, unfortunately. So if our total volume is this, and if we apply just an average volume loss that we've seen the last few years, and that's assuming that these high temperatures stay the same, we would estimate a disappearance by 2060 or so. That's kind of a rough back of the envelope estimate of how long we might think Kathlyn Glacier to be around. Personally, I think it's going to be around in some way, shape, or form a little bit longer than that, but by mid-century to 2070 for sure, likely would be a disappearance date for Kathlyn. To wrap things up, I want to connect things to water and to why the loss of ice matters and what we need to do moving forward, and hopefully a hopeful story and an opportunity for management practices moving forward. So this is a figure from this study by Andrew Fountain and Wendell Tangborn, which was really the first to show what theoretically happens when we lose glaciers from a watershed. Here you've got a theoretical watershed with 14% glacier cover, and here a theoretical watershed with 0% glacier cover. And the main takeaway here is that at the end of summer and early fall, when you have glaciers, they're still available up there. There's still ice available up there to melt and contribute to your streams and rivers. When we lose that, in the later part of our summer and early part of the fall, we don't have that reservoir of ice sitting up there to contribute to rivers and streams. The seasonal snowpack has largely melted. It's a drier part of the year. It's a hotter time of the year, and that ice reservoir is gone. So we're slowly moving from a state similar to this to a state like this, where this one part of the year is going to be critically impacted. And so now let's zoom in on Toboggan and think about why this matters for our local watershed and what we might be able to do locally and how we might think about this more broadly in a world where we're losing our snow and ice. So what you're going to see here is some information from a couple of studies, local studies on Kathlyn Lake and Toboggan Creek. So Toboggan Creek has an interesting story. Long history of forestry and agriculture. A lot of people live there, call it home. A lot of water use licenses and a significant source of residential drinking water. A hatchery since 1985. So we have a lot of folks using, relying, living in and on Toboggan Creek. This study concluded it's a highly productive system, but it's facing several impacts: transportation corridors, logging, and agriculture. Riparian areas heavily impacted. One of the 5 most severely impacted Bulkley River tributaries. So an interesting study looking at the kind of the net impact and the user groups of Toboggan Creek. And at the head of that, we have our glaciers contributing to it. I'm showing you this to focus on Toboggan Creek, but also to know and to think critically that every basin is going to be unique. As climate changes, as temperatures rise, as glaciers and snow melt, every basin is going to have a different and unique response and have to have a unique management strategy moving forward. This study focuses specifically on Lake Kathlyn. So since 1994, we've been diverting meltwater into Club Creek and into Lake Kathlyn for the purposes of keeping Lake Kathlyn dissolved oxygen at an appropriate level, keep temperatures cool in Lake Kathlyn. That license is for less than 12 cubic feet per second to be diverted. And what I've found in the reading I've done, and some of you may well know more than me, but that's been more about 6 cubic feet per second being diverted from Glacier Gulch into Club Creek and down into Kathlyn Lake. So we are removing water from Toboggan Creek into Lake Kathlyn annually, and we've been doing so since 1994. To put those numbers in perspective, this is the total amount of water that's been coming off annually. So the magnitude of water we've been diverting into Lake Kathlyn has been similar-ish to what comes off of the glacier every year. So important to put that in perspective in terms of the volumes we're thinking about here. Right? So the vast bulk, or up to half of what melts off of Kathlyn Glacier in any given summer, we are redirecting into Lake Kathlyn away from the Toboggan Creek watershed. And this paper concluded it is important that the seasonal diversion of glacier water into the lake is maintained, right, for the health of Lake Kathlyn. As we've seen with the modeling, this won't be an option in perpetuity. We won't be able to do this in a few decades down the road. We're going to have to do things differently. We're going to have to think about all the different user groups around Lake Kathlyn, within Toboggan Creek, and think critically about what this looks like moving forward. Another thing I like to do, or I've done a lot of, is model stream temperature as we lose our snow and ice, and see what that's going to do and how that's going to impact our freshwater ecosystems. So what you're looking at here is modeled stream temperature for Toboggan Creek. This is a model of historical, what's called maximum weekly average temperature, right? So average maximum temperature for a whole week. And then this is projections of what that stream temperature might do given our different climate scenarios moving forward. Blue here are some different thresholds for salmon from some various publications. And the 4 diamonds here are some observations from 2002, some of the stream temperature data I was able to find. I would love to find more to calibrate this model. The main story I'm showing here is that we're likely to be moving into temperature regimes that are getting more stressful for salmon. Not terrible by any means. We're in this or close to this optimum temperature range, but moving upwards towards species assemblage thresholds, which means once you cross this line, that temperature is favoring other species and not salmon, right? So a story moving forward that is important to characterize and understand better for Toboggan Creek. All right. Everything in context and then some takeaway messages. So this story of glacier loss is happening globally. This is from a paper by Arounce et al. 2023. The red dots here are showing a dramatic loss to the end of the century. Okay, so nearly losing all of the ice. And for our part of the world here, we're seeing a lot of dots that are red. Okay, so forecasting what's happening at Kathlyn, where we're going to lose most of the ice. But they also concluded that every 0.1 degree C matters, right? So our efforts to reduce carbon, methane emissions matters in terms of how much ice we're going to have by the end of the century. This is from a paper by a group at Arizona State University documenting this unprecedented continental drying, okay? Ice mass is melting, snow melting, and also the loss of water from aquifers, underground aquifers, and evaporation is yielding a really big change in our hydrologic system. We are moving from a heck of a lot of water on the land, and we're dumping it into the ocean, basically. Right? These areas in red show the hot spots around the globe of where we're getting most of this drying, this continental drying. Okay, so we have this story of long-term loss of water from the land going on. However, we have some important positive stories. This is Kara Pittman's work from 2021. There are going to be some watersheds that are going to win. They're going to improve as the glaciers get smaller. So basins where we have so much ice that the water is so cold that salmon can't utilize them. This study was looking primarily at valleys where there's a huge glacier there presently, and in the future there won't be, and so there will be a river system, potential new salmon habitat. Right? And most of those basins with huge glaciers are up here, more in the St. Elias, Wrangell-St. Elias, coast of Alaska region, and very little down here where we live. However, we're going to have climate winners where we live too. We're going to have basins where we live that are going to be more resilient than others, and we need to be able to identify them and manage them as such. Another quote to frame this is from Jonathan Moore and others at SFU. Stewardship of glaciarized landscapes and other ecosystems that are being transformed by climate change urgently need forward-looking science and environmental policy. So with a clear-eyed vision of what we're looking at in the coming decades, we need to kind of reframe or holistically, completely reframe how we are managing our watersheds and our basins. So a few key takeaway messages to wrap up. We're seeing increasing rates of Kathlyn Glacier mass loss and recession. This is in line with what's going on regionally and globally, and it's driven largely by increasing summer temperatures, decreasing winter precip, and a darkening of glacier surfaces. Modeling reveals that we will probably have an earliest date disappearance of Kathlyn Glacier by roughly 2060. However, Kathlyn Glacier is thicker than the models think, than the models know, which is good news. And this date, I want to do a bit more refined modeling, and this date, my guess is more towards the later end of the 21st century. Some semblance of Kathlyn Glacier will still be present. We have to adapt. We know this is coming. We have a bit of lead time over the coming decades to adapt within our management strategies of these watersheds, but also that mitigation still matters. Every 0.1 degree C that we can avoid of temperature rise makes a difference and keeps more ice on our landscape. And we have an opportunity, I think, with this knowledge moving forward. We need these watershed-specific studies and adaptation practices to build resilience into our watersheds. Also, we can identify, manage, and protect basins that are of particular importance. Glaciers that have more ice today are going to be these thermal refugia for salmon and other creatures moving forward, and we can proactively manage them today. There's more work to be done. So hopefully, I'm excited to continue glacier monitoring and refine the modeling from it. More modeling and observation needs to be done in the Toboggan Creek watershed to better understand the story for Toboggan Creek. There's some really important known unknowns. Snowpack is going to be becoming more and more and more important, and we need to do a better job of monitoring that and the spatial distribution of snowpack. The role of groundwater is a big known unknown. And we've got some critical questions to think about locally, taking Toboggan Creek as an example. What do we do with the Lake Kathlyn Club Creek diversion? Do we change that? Do we alter that? It's an important question to ask. Residential and agricultural water use, does that need to change? Are we going to have less water to go around? What's the resilience of the hatchery moving forward? What can we do in terms of riparian habitat remediation? Right, so some critical questions to ask moving forward. And I'd say there's a lot of work to be done. And yeah, hopefully that's a positive message on this. There's tons of employment for these young, brilliant scientists to get out there in the landscape and do some important, necessary work. So the work we did with the radar was made possible by funding from the Alpine Club of Canada and also the Wet'suwet'en community for us. So folks that stepped up and helped fund this and helped provide the opportunity for the students to get up there and do that work with us this last fall. I'd encourage you all to get up to your glacierized landscapes and enjoy them. They're beautiful places, they're important places, and having one in our backyard is super, super important and cool thing to have. Thanks, everybody. Depends on the frequency of the radar. So one thing I'd like to do is go back with a different frequency. We were using a 100 megahertz frequency radar system, and we were struggling at those higher depths. We need a 50 megahertz system at a minimum to get a more reliable depth measurements. But on bigger glaciers, you're using a 10 megahertz system. So the lower the frequency, the deeper the ice you can penetrate. But they're using similar radar systems on Antarctica, Greenland, but just different frequencies. Hundreds of meters, many hundreds of meters. It depends too on the thermal characteristics of your ice. So this glacier, Kathlyn Glacier, other glaciers here on the coast are wet, and it's more difficult to penetrate. Drier ice, you can penetrate even further. So Taku is another glacier I've worked on up in Southeast Alaska. I don't know if it still is, but at the time it was measured as one of the, if not the deepest mountain glacier ever measured. So the surface of the glacier where we were doing research was about 1,300 meters, and it was 1,500 meters deep, meaning that the bottom is below sea level, and that as it melts, it'll be a big fjord as it goes back. The earliest measurements, though, from that were done with seismic technology, where you set off an explosion and you have geophones that measure the reflection off the bed. Yeah, thanks. Like for me growing up in Alaska and having a glacier I could see from my parents' house was just, it was just this amazing, cool thing, and I wanted to go climb on it. It wasn't like it's changing, or it became that as I got into glacier science and studying it. And for me, what gets me every time I go up to any glacier repeatedly is the dynamism of these amazing features, like how much they change. It's weird to process it because I get excited when I go back and I see how much change. I was like, oh my gosh, that's amazing. Even though, and then I process it a bit, I'm like, oh my gosh, that's amazing. That's not good amazing. That's bad amazing. But I'm blown away by the landscape up there, how amazing and dynamic it is, how changing it is. And you don't see that unless you go and visit these glaciers repeatedly and regularly. And so having the opportunity to do that as a kid was really impactful. Yeah, it helped me go and yeah, do what I did or am still doing. And I think too, like having a glacier story that we as a community can tell to a wider audience to make that change more real, I think can be powerful. And that's part of what many have done for many years to kind of try to communicate what's going on with regards to climate change. There, I wouldn't be able to give you specifics, and that's out of my wheelhouse. That would be more of a paleoclimatologist or a dendrochronologist that could tell you that story more. But Little Ice Age, you know, the build up to that started hundreds of years ago. It varies where you are on the planet. A lot of thinking now is that it came from what's called the Maunder minimum. So you had a period when our sun was in a phase that was more quiescent. It was quieter. There weren't as many sunspots. And that net over many decades led to less radiation, less energy. And we had a cooler, wetter period. So that's, I wouldn't be able to put any numbers on it, but you know, winters where we had more snow, right? And then summers where it didn't melt that much. Wetter summers, cooler summers where you just had persistent snow, or where you would get to the point where, you know, 60% of, you know, to have the glacier in balance, you know, more summers where 60% of that glacier was covered in snow. You know, 2 meters of mass gain at the top versus 2 meters below, and it kind of balanced out. But yeah, sorry, I can't put any more numbers on it. You have to ask.
And it doesn't say how to be extreme, like it just needs
No.
to get into the gain side of the balance.
That's a good point. And so if we go back to, like, say, we had a period in, and it's well documented here in Western North America, in the 60s, 70s, and 80s, we had a period where some smaller glaciers even advanced. And so if we go back here to the 60s and 70s, and we look at what was going on with regard to temperature. So on this, I've got actual temperatures. So 60s and 70s are the moving average here is about, you know, 12.75. And then up here, we're at about, so that's almost 2 degrees on average cooler in the 60s and 70s. Similarly with precip, we had a heck of a lot more winter precip. And at that time, glaciers were actually growing, either staying static or even growing and advancing in some cases here in Western North America. So we don't have to go back actually that far to know and understand what climate needs to be to have our glaciers be in balance. And it's, you know, it doesn't seem like 2 degrees is actually quite a heck of a lot when we think about climate change. But that's not that far back in our distant past, right? Some perspective on what it would mean to have a climate that would rebuild or at least you know, move back to a steady state. Yeah, if I answer, so few answers to that question. So one, flow is proportional to thickness. So thicker ice will flow faster. We also have surging glaciers. These are interesting, unique phenomena that don't occur in very many places. And what a surging glacier is, basically think of it as a burp of volume, where you've got a lot of accumulation up here, and then it builds up, builds up, builds up. And there are various theories of why it really dramatically flows to lower elevation. Some think it's precipitation and water at the bed that rapidly, you know, speeds that up, and you get this surge. So there's a number of these glaciers in far northwestern BC, coastal Alaska, other places around the planet. There aren't very many of them. We would not see that at Kathlyn. We wouldn't see that here, but that's something that happens to this dramatic redistribution of mass. In general, as our glaciers thin and get thinner and thinner, the flow decreases. So we get to these more stagnant ice masses that aren't flowing much at all, and just kind of melting away and not flowing. Yeah, and to be quite honest, when I was trying to find a map of the basin, I really struggled to figure out the history of what's gone on. It's a really, yeah, it's a very strange basin. There's a lot of interesting things that have gone on in terms of water diversions and trying to understand and think about how we manage or think about Toboggan Creek moving forward is complicated by all these things. Anyway, yeah, and this map of streams, which you can't really see on here, is this was created. This isn't even actually totally accurate in terms of where the streams are. This is based on a digital elevation model and doesn't really take into account our diversions. Anyway, yeah, it's a very complex system that's been heavily modified by us. I mean, at this point, this is just me trying to feed in what I've gleaned from the glacier and try to share it with the larger community and start a process of thinking about some of these critical questions. Yeah, seeding a conversation more. Some things that I would like to do from a glacier standpoint that feeds into the water picture is that I want to start monitoring this flow. So there's a really nice little this little bedrock pinch point. All the water flows right through there. It's a perfect spot for monitoring the total amount of water coming off of Kathlyn Glacier. Some of my previous work, I've done a lot of stream temperature monitoring. I'd like to communicate with toboggan hatchery folks and see what kind of data is out there and how we might supplement what monitoring's going on to get a better picture of what's happening in the Toboggan Creek watershed. And there's a lot more work going on kind of in the back. I'm partnering with Michael Price and folks at Skeena Wild and Johanna at Eclipse in terms of a broader study to try to identify these basins of resilience and thinking, how do we manage our basins moving forward with the understanding that they're changing, with the understanding of how they're likely to change. So here, I think you're referring particularly to Bruce Jack Mine, probably. So I teach field schools at Coast Mountain College, and so I've been fortunate enough to go up there about 4 times with students and see it. And I also taught the 2 students that now run the glacier monitoring program there, which is kind of a cool full story thing that you mentioned. Anyway, all that being told is, I don't know if you've seen it on satellite image or pictures, and I don't have any photos to show you now, but the road, if you look at it in the summer, it's down in a trench, right? And that's for a variety of reasons. So as they're maintaining that road throughout the wintertime, they're plowing the glacier road and removing snow from it. And so once the melt season starts, that trench where the road is doesn't have any seasonal snow to protect it, right? So as soon as the melt season starts, you're starting to melt down where the road is. Another part is the changing of the color as well. And so every, I don't know how many it is, 2 to 4 years, Bruce Jack has had to move the road, right? So through the grading process, then the channelization of the water. So it's kind of a nightmare of trying to maintain it. The ice is a pretty workable medium. So who's seen it firsthand, the Bruce Jack Mine Road? So like the graders that are up there and the excavators like moving ice and filling holes so that big trucks can just drive up it. So yes, it's exacerbating the melt. I don't think it's that much. They're not privy, or they don't share their data. So I don't know, but having looked at it from remote sensing data, I actually don't think it changes it that much. As they're piling that snow on the side of the glacier, you're also protecting these big mounds of ice to the sides of the road with all that ice they're plowing up. So you get this really weird, funky shape on the glacier. But all told, I would guess the volume loss by that operation, I would guess it's not huge. Good question. So the Pacific Decadal Oscillation is this pattern in the North Pacific. We can go back to temperature data here to kind of look at that. And so we have a lot of these atmospheric patterns that oscillate between phases. And one that you might be most familiar with is El Nino, the El Nino Southern Oscillation that goes back and forth between El Nino and La Nina. warm phases and cold phases, and these have impacts on our weather. The Pacific Decadal Oscillation is a pattern in the North Pacific that instead of operating on a 2 to 7 year scale, which is the El Nino Southern Oscillation, it operates on a multi-decade scale, so 20 to 30 years. And so we've had some interesting changes with the Pacific Decadal Oscillation over time. And if I can remember some of these key years, so 1996, there was a really key change, and we kind of see the pattern of our weather changing there. 1976, there was also a key change right here. So those patterns influence the weather that we experience, from warmer and drier to cooler and wetter. The short answer is yes, it definitely impacts things for sure. It impacts our weather. With these different patterns, as climate progresses and gets warmer and warmer, we're kind of starting to see outliers where what we're seeing on the ground, the weather we're seeing doesn't quite match exactly. Like, for example, this is a La Nina year, right? Typically in a La Nina year, it's colder and wetter. And we've had some signs of that. There's a lot of snow at Shames up above Terrace this year. But compared to La Nina years 10 years ago, it's nothing like it would have been in the past. So I don't know what's going on with the Pacific Decadal Oscillation at the moment. I think we've shifted back to the negative phase, if I'm correct. But more of what we're seeing here relates to this global pattern of really dramatic temperature rise in the last few years, connected by a number of things. El Nino, global emissions going up, but also if this masking effect that sulfur dioxide emissions had from shipping. So basically, we cleaned up our act in terms of these pollutants in the atmosphere from shipping, and that sulfur in the atmosphere was blocking incoming solar radiation. We cleaned up those ships, we made them cleaner, but in doing so, we removed that solar shield, if you will. And so that's part of the theory of what's going on with this dramatic increase in these last 4 years. That's also contributing this increase. So yes, these oscillations, these patterns in the coupled atmosphere-ocean circulation system matter. I don't know how much it matters at this point. I would say the PVO is less impactful now than it was 10, 20, 30 years ago.